Good morning, everyone. My name is Kira Proctor, and welcome to our 10th webinar of 2022. Our series of webinars have been running now since 2020, and if you've missed any, you can go back and review them all on demand right here on our YouTube channel. Today we're running our second RIBA assessed webinar, this time looking at design and specification criteria for passive and low energy use housing. This presentation will introduce how we design housing with low energy use in mind, and how the principles and guidelines of the Passive House Standards can inform that. Whilst the Passive House Standards themselves provide an excellent framework for low energy design, the strategies they embody can be applied to benefit all housing, regardless of the regulations and assessments applied. So we'll begin today by taking a look at what those principles are and what requirements and standards apply to meet Passive House certification. We'll then move on to consider how these concepts can be applied in a more general context, bringing the benefits of low-energy design to all types of projects. The Passive House regulatory framework originated in the late 1980s with ideas developed by Bo Adamson of Lund University, Sweden, and Dr. Wolfgang Feist of the German Institute for Housing and the Environment. These research projects led to the construction of several experimental homes in the German city of Darmstadt. Building on these early 90s experiments, Dr. Feist founded the Passive House Institute in 1996 with the aim of developing and refining this concept and ultimately promoting its use around the world. From the first projects outside of Germany in the early 2000s, Passive House certified buildings can now be found all over the world. The actual standard itself, however, only codifies a set of principles that have been applied to buildings for a considerably longer time, even back as far as the Middle Ages, albeit in a far less refined form. As building regulations have developed and energy performance become a more important consideration, elements from the passive principles have become more and more integrated into modern homes and are increasing beyond high-end self-build to be part of mainstream housing practices. There are 5 basic principles: thermal insulation, thermal bridge-free design, airtightness, ventilation with heat recovery, and passive house windows, or more generically, high-performance glazing. The purpose of designing according to these principles is to minimise the energy inputs required to maintain a comfortable indoor air temperature. Ideally, the space heating and cooling energy requirements can be reduced to the point that passive sources source as solar gain and heat from the building occupants and are sufficient for most of the time. The Passive House Institute provides software known as the Passive House Planning Package, or PHPP, to calculate these energy loads, and provides prescriptive guidance and details along with product certification. Whilst this approach certainly simplifies the process and ensures rigorous adherence to good or best practice, it does not always allow designers the necessary flexibility to balance the full range of project requirements. In such cases, the Passive House guidance and principles can be viewed as best practice recommendations for designing buildings assessed by other means such as national building regulations. The Passive House guidance itself is a fully open source and fully available, so there's no need for official approval to undertake a Passive House project. That said, the verification and certification services provided by the Passive House Institute can serve to greatly simplify planning and approvals process for such buildings, and reinforce confidence and trust with subsequent buyers and sellers. So let's now consider how the 5 basic principles can be applied, and what they mean. Thermal insulation. Thermal insulation is what limits the loss of heat from the building envelope, and is the cornerstone of the fabric-first approach to building design. This approach seeks to maximise the performance of the basic components of the building, rather than relying on mechanical or electrical systems. The fundamental physical property of insulation material is their thermal conductivity, also known as the K value or lambda value. This property measures how well heat can flow through the material by conduction. In this mode of heat transfer, the heat energy is transferred between the individual molecules of a material by direct contact. Because of this reliance on physical contact, there's a correlation between material's density and its thermal conductivity. Therefore, less dense materials such as foams and fleeces are less able to conduct heat than denser materials like bricks or concrete. Bricks, for example, have a thermal conductivity of 0.77 watts per metre Kelvin, whilst aerogel insulation is far lower at 0.015 watts per metre Kelvin. Some materials, for example blown rigid foam insulation, may have a thermal conductivity that varies over time as blowing agents escape from the foam structure, so it's important to ensure the correct thermal performance figures are used. Third-party product certification or UKCA documentation will typically give aged performance values if they're relevant to the application. Thermal conductivity, however, only looks at the basic material. It doesn't account for the thickness. To factor in the material thickness, we take the thickness in meters and divide it by the thermal conductivity to give us the thermal resistance, or R value, in meters squared Kelvin per watt. The next step is to convert that into a value for an entire wall, for which we use the thermal transmittance, or U value, which is the inverse of the sum of the R values for the different layers in the construction. U values are quoted in watts per meter squared Kelvin. Where R values vary proportionally to thickness of materials, U values do not, so as we move to lower U value, we need to add exponentially more insulation to improve them further. As an example, the limiting fabric parameter, more commonly referred to as the backstop or worst permissible U value for a wall, given in approved document L for England, is 0.3 watts per meter squared Kelvin, and the recommended worst case for passive house is 0.15. The best practice passive house value is considerably lower at 0.06. In practice, compliance with either standard is more complex than achieving a simple maximum U value, but roughly speaking, the worst case U value for a passive house would be considered pretty good under national building regulations. A thermal bridge occurs either where a material of higher thermal conductivity intersects a less conductive material, or where building elements join, such as at floor zones or corners. Thermal bridges have two principal negative effects. Firstly, they increase the overall heat loss by providing an easier pathway for heat to escape, and secondly, they create cold spots internally. Condensation and mold growth can occur in these areas, which has a detrimental effect on the indoor environment. The first of these, typically where structural elements like studs in a timber frame wall intersect the insulation, is accounted for via an adjustment in the U value calculation. This takes the thermal conductivity and proportional area of the bridges and adjusts the U value accordingly. If we consider a 140 mm thick panel of rigid foam insulation, if we use this in a typical timber frame wall, the U value when adjusted to account for cold bridging at the timber stud will work out to around 0.22. On the other hand, if we eliminated this cold bridging but using the same thickness of insulation in, for example a structural insulated panel system, the U value drops to 0.15, purely due to the lack of repeating thermal bridging at the studs. Thermal bridging at corners and junctions is accounted for using an additional value for linear thermal bridging, known as a psi value, but in most cases these are addressed using standardized pre-assessed details to limit heat loss. The easiest way to visualize the way thermal bridge-free design works in practice is to simply imagine drawing a pencil line around a cross-section of the entire heated envelope of a building. If that can be done without touching anything other than insulation, the design is free from thermal bridges. Because of the adverse effect that thermal bridging has on both the U value of individual elements and the overall energy performance, whether assessed via PHPP or SAP, reducing cold bridging in low-energy building is a matter of not just principle, but also practicality. Getting U values anywhere close to passive house best practice performance levels without restricting thermal bridging is virtually impossible. But even in cases where designers are aiming for lower standards, the benefits regarding limiting localized condensation are clear. Whatever the assessment criteria, high-performance insulation systems like those that incorporate aerogel insulation have a very important role to play in minimizing thermal bridging by allowing the thermal resistance to be maximized at any given point. In locations such as window reveals and door openings, it can be difficult to maintain a similar level of insulation to that found over the main sections of a wall, leading to these areas being relatively cold. In extreme cases, this can cause the temperature to drop to the point where condensation may occur in these areas, and as fabric insulation levels increase, so does the importance of continuity and uniformity. Ultra-thin internal wall insulation, IWI systems that use aerogel insulation provide high thermal resistances in minimal thickness, allowing for a more uniform envelope of thermal insulation performance and minimizing localized drops in R values around complex features. The fire-rated IWI systems also allow this continuity to be maintained where reduced combustibility is required, offering significantly higher performance per unit of thickness than conventional fire-rated insulation, such as mineral fibre. Fibrous insulation quilts typically have a thermal conductivity in the range of 0.035 to 0.044 watts per metre Kelvin, whilst aerogel is 0.015 to 0.019, meaning like-for-like performance can be achieved in less than half the thickness. While big thicknesses of insulation are expected and accounted for in passive and low-energy projects, it's not always possible to maintain such thickness over every part of the structure. Aerogel insulation systems can allow this uniformity to be achieved, and being of comparable permeability to fibre quilt, to be achieved without compromising moisture movement. This need to create uniformity of insulating values and preventing cold spots is also an important aspect to consider when specifying the windows in low-energy and passive projects. When using systems such as aerogels, all product details and installation practices should be reviewed in the context of the Control of Substance Hazardous to Health 2002 regulations. Manufacturers' installation guides and material safety data sheets should be consulted, and such products may require different installation practices when compared with traditional insulation materials. Therefore, specific data for the specified product should be reviewed. Likewise, the fire performance of the system should be considered. The facing boards used in laminated systems such as plasterboard or magnesium oxide are typically classified as A1 or A2 under the EN 13501-1 standard. This means their reaction to fire will comply with all approved Document B standards for linings. However, some specific situations such as relevant buildings, as defined in Regulation 7, may have additional fire rating requirements. Most commonly, this is a consideration in building over 18 metres in height in England and Wales or 11 metres in Scotland. In such cases, all materials which become part of an external wall or specified attachment must achieve Class A2-S1D0 or Class A1, other than those exempt by Regulation 7.3. While raw silica aerogel is inert and non-combustible, fibrous composite aerogel insulation of the type typically used in construction applications is available with a range of reaction to fire classifications, from Class C to Class A1, depending on the fibrous carrier matting used. For context, most mineral fibre insulation products fall into Class A1 or A2. Passive and low-energy homes must pay particular attention to the specification of windows used, as poorly insulating windows can not only affect the overall heat loss, but as with cold bridges, can also create cold spots and cold radiation. This phenomenon occurs when the influence of a cold surface can be felt nearby, often leading to a perception that a space is colder than it normally is. Even by utilising multiple layers and glazing, inert gas fills and thermally reflective coatings, windows still typically fall a long way short of the performance of the rest of the building envelope, with the passive house specifications calling for windows with a U value of 0.8 metres squared Kelvin per watt or less, significantly above the opaque elements. Windows are also important to provide heat input to the building via solar gains, and for this reason passive houses in heating climates like the UK tend to position the majority of glazing facing south in order to maximise this effect. This requirement to maximise collection of solar heat has to be carefully managed though, as highly insulated and airtight homes can be susceptible to overheating if this is not carefully assessed and managed. It's a common misconception that passive houses do not have opening windows, but in fact the specifications call for at least one opening window per room in the living spaces. Opening windows is among the most cost-effective and simple means of counteracting overheating, and is useful to prevent poor indoor air quality in exceptional circumstances such as large gatherings. That leads on to the next concept we need to consider, the airtightness of the structure. It's often said that airtight buildings can be like living in a plastic bag. However, this is a fundamental misunderstanding of what we mean by airtight buildings. Reducing the air leakage simply means eliminating sources of air infiltration and exfiltration over which we have no control, drafts in other words. A good supply of fresh air is a critical component of healthy indoor environments, and the passive house specification is designed to ensure this is facilitated by controlled and carefully managed ventilation systems with carefully considered impacts on energy performance. Uncontrolled air movement, on the other hand, should be reduced as far as possible. As we've already covered, the thickness of insulation layers increases exponentially with reductions in U value, and after a certain point this becomes both uneconomical and impractical, even in explicitly low-energy buildings. So it's very important that every other factor affecting energy performance is controlled and limited to minimise energy usage. In dwellings, there are two main drivers of air leakage: the internal stack pressure caused by the relative buoyancy or warm air and resultant convection, and external forces from the wind. Because warm air is less dense, it will rise upwards in a building and can leak out of any air pathways found at higher levels. Correspondingly, as this air rises, colder air must be drawn into the building lower down. As the warmer air will contain significantly more moisture, this outward air leakage could lead to condensation issues as the air leaking cools and deposits liquid water. The cooler air entering the structure lower down will lower the internal temperature in the building, necessitating energy input to maintain the temperature of the habitable space. Externally, the wind forces acting on the building will have similar effects, but instead of the pressure gradient working from top to bottom, it will be aligned to the wind direction. Cold air will be pushed in on the windward side where there is a positive pressure, and warm, moist air sucked out on the leeward side where the pressure is negative. Limiting this air movement is a critical part of low-energy design, as even highly insulated buildings will have poor energy performance if the movement of air is not controlled. Both the building regulations and Passive House standards therefore include pressure testing and minimum performance levels, but there are some important differences. The UK building regulations use a pressure test result known as AP50, which is the volume of air in cubic metres that flows through the building fabric area in square metres in 1 hour, when a reference pressure of 50 pascals is applied. This pressure can be applied in either direction, by pressurising or depressurising the building. The backstop value for this is 10 metres cubed per square metre per hour in England, Wales and Northern Ireland. In Scotland and the Republic of Ireland, the preferred or reasonable limit is set at 7, and while it's theoretically possible to comply with a higher value, the necessary trade-offs will generally be unacceptable. Passive House expresses the air leakage differently, using a standard called N50, which is the air changes per hour through the building's internal heated volume, at the same 50 pascal reference pressure. In Passive House tests, however, the pressure must be applied in both directions, pressurising and depressurising the building, and the two results averaged. The test equipment and physical procedure is largely the same for both AP50 and the N50 test, so it's perfectly possible to run both simultaneously. But the way the final results are calculated is sufficiently different that conversion between the two is just not possible without access to the source data. The BRE's Passive House Airtightness Primer document, highly recommended as follow-up reading, gives a useful analogy to illustrate the difference in standards. A building with an air leakage rate roughly meeting the UK regulations limiting value of 10 metres cubed per square metre per hour, AP50 will have gaps and cracks equivalent in area to 1/20 pence piece per square metre of the floor area. In contrast, a Passive House meeting the required 0.6 air changes per hour N50 standard will have gaps equivalent to an area of a 5 pence piece every 5 square metres of floor area. Airtightness and vapour control. There are numerous ways of making a building airtight, and finding the most appropriate method to apply it to a given project is usually a matter of balancing a variety of competing requirements. The most important of these is considering the effects of reducing air leakage on the transfer of moisture around the building. Historically, most buildings had high levels of airflow, both intentional and incidental, for example from open chimneys. Modern buildings where this airflow is not present require more careful, holistic consideration of hydrothermal properties in relation to air movement. Some building materials such as cast concrete, cross-laminated timber and structural insulated panels have an inherent advantage when it comes to air leakage, as the basic materials involved have low air permeability. Others, like blockwork or brickwork, are more permeable, so require additional measures to control air leakage. In all cases, though, junctions, services and the nature of the on-site assembly process still pose challenges to achieving a low air leakage rate, even when using the most impermeable base materials. The air leakage performance cannot be considered in isolation, and in parallel is critical to address moisture control. This is covered by Part C in England and Wales, Section 3 in Scotland and Part F in the Republic of Ireland. It's also Part C in Northern Ireland, but this is a different set of regulations to that used in England and Wales. In all 4 cases, though, specifiers are referred to the British Standard BS 5250. This document, the most recent edition of which is BS 5250-2021, is the Code of Practice for the Management of Moisture. Prior to the 2021 edition, this was simply control of condensation. However, this has now been expanded to cover all sources of moisture that can affect buildings. This reflects an increasing recognition that the effects of heat transfer and the flow of air and moisture around structures are interlinked and should be considered holistically at the design stage. To this end, the standard also defines connective and systemic effects. Connective effects being the effects of changing conditions at junctions between different building elements, and systemic being effects of an action on the whole building or parts not directly connected due to changes in the hygrothermal condition of the inside of the building. Both these serve to raise awareness of the interconnected nature of moisture in buildings, although standard does note that assessment methods for the impact of these effects is currently at an early stage. BS 5250 gives detailed prescriptive guidance and example constructions for various wall, roof and floor types that are, in effect, tried and trusted and therefore do not require verification by calculation. It does, however, also provide guidance and methods for undertaking such calculations should they be necessary. We'll move on to discuss these calculations shortly, but firstly, let's consider some of the definitions given in BS 5250-2021. When discussing air and vapour control layers, or AVCLs, BS 5250-2021 lists these important considerations. Most obvious is the performance required by the AVCL. This is important as the AVCL is not necessarily a standalone product or system, with BS 5250 giving specific examples of glass, metals or plastic floor coverings as of themselves constituting all or part of a vapour control plane. The assessment guidance can therefore be used to determine the performance needed to control the risk of condensation, and we'll discuss these methods shortly. Note 2 in this section discusses the need for additional materials to control air and vapour movement, but it should be stressed here that such dedicated AVCL materials are not a hard and fast requirement. If it can be demonstrated the materials forming the element can inherently minimise moisture risks, then a specific AVCL can be omitted. This also leaves a variety of options for managing these risks open to designers, depending on the nature of the building fabric and its intended use. The second important consideration is the practicality of installation, basically how easily the theoretical design can be realised on site. BS 5250-2021 introduces the concepts of ADT performance, or as designed theoretical, and ABIS performance, as built in service. This is an important distinction as these can be very different. In terms of AVCL performance, this relates mainly to the simplicity of sealing laps and penetrations, and whether or not the need for complex and difficult installation processes can be designed out. It's also important to ensure the design and subsequent installations are robust enough to meet their lifespan requirements. Lastly, in Notes 3 and 4, BS 5250-2021 illustrates the many forms air and vapour control layers can take. In essence, every layer in the building element plays a role in the management of an air and vapour transfer to some extent. Assessing and balancing the performance and practicalities of each part is key to a successful design, and this is particularly true at the higher levels of performance required by passive and low-energy buildings. Note 4 also clarifies that while most specific ACVL membranes tend to be impermeable to both air and vapour, it's also possible for membranes to be airtight yet vapour permeable. This again gives designers important flexibility in where they position and how they install the airtight layer, as the air control and vapour control functions can be separated and performed by a variety of components throughout the element. We'll come back to this later, but now let's consider the assessment of vapour transfer. BS 5250-2021 references 2 standards for condensation risk, BS EN ISO 13788-2012, hygrothermal performance of building components and building elements, internal surface temperature to avoid critical surface humidity and interstitial condensation calculation methods, and BSEN 15026-2007, Hygrothermal Performance of Building Components and Building Elements, Assessment of Moisture Transfer by Numerical Simulation. The simplified Glaser method, given in BSEN ISO 13788-2012, is considered by BS 5250 to be generally acceptable for most types of constructions. However, BSEN 15026-2007 can be used to gain greater detail as to the hygrothermal performance. In the Glaser method, the thermal and vapour transfer properties of the various materials and simplified environmental conditions are used to model the temperature gradient through the element and also the dew point line. Dew point is the temperature at which the air will become saturated and condensation will occur. In our example wall here, a cross-laminated timber panel with insulation external to the structure, the dew point will generally occur in the outer ventilated cavity, if at all. This is because the insulation is positioned such that it keeps the more vapour-resisting inner layers warm enough to prevent condensation. This makes this type of wall a very robust hygrothermal solution where high levels of insulation are required. Let's now move on to consider how the positioning of construction membranes in a wall affect the required performance characteristics. Firstly, we have the traditional vapour control layer position on the warm side of the insulation. This is the most common approach historically, and membranes used in this location are usually airtight and vapour impermeable. This approach works by ensuring warm, moisture-laden air cannot reach the colder outer parts of the wall construction where it can condense. Variable vapour resistance membranes have become available that can become more or less vapour permeable in response to environmental conditions. These membranes block the passage of moisture vapour in winter when condensation risks are highest, but allow some degree of moisture transfer in warmer summer conditions. This can help the building fabric dry out in either direction, helping remove construction moisture and moisture from external sources such as rainfall. The principal downside to this location of membrane is in the detailing and sealing required during installation. Internally, there is substantially more penetrations for services and structural elements. While this can mitigate to a certain extent by using service voids, relocating service runs away from external walls or using a variety of tape sand gaskets, this still introduced additional complexity throughout the process. If we move the airtight layer to an intermediate position in the construction, such as over a structural insulated panel, or, as shown here, over cross-laminated timber, we can greatly reduce the number of services that need sealing, and possibly also simplify sealing membrane joints and laps, as there would typically be a more solid substrate to fix against. If the membrane is self-adhesive, this process becomes easier still. On the other hand, moving the membrane to this position does mean the vapour permeability must be considered more carefully. In our CLT example here, the membrane can either be vapour permeable or vapour tight, as the majority of the insulation will be further outside. The precise level of vapour resistance needed will depend on how vapour permeable the CLT panel is. If the panel has sufficient vapour resistance to limit condensation risks, then a vapour-tight membrane may not be required at all. If there is insulation present on the warm side of this membrane though, such as in a SIP wall or timber frame, then the membrane should be vapour permeable to prevent trapping moisture within the insulation layers. This is particularly true if additional layers of insulation are specified in a warm frame construction. Positioning the vapour-permeable airtight layer in this location, with insulation to either side, makes the correct balance of vapour permeability throughout the construction very important, and project-specific condensation risk analysis calculations are recommended. If additional detail or analysis over a multi-year time period is required, the EN 15026-2007 method can be used. But it should be recognised that these calculations require a higher degree of experience and expertise to undertake than the simpler Glaser method analysis. The final possibility for the location of the membrane is outside the heated envelope in the cavity behind the outer cladding or rain screen. Being on the cold side of the insulation, membranes in this location must be vapour permeable to prevent trapping moisture, and weather resistant to provide temporary protection during construction. Providing this temporary weather protection means there will often be a membrane in this location, regardless of air and vapour control requirements. So, if the airtight layer is positioned elsewhere in the construction, a membrane in this location need not necessarily be airtight, although it may help reduce convective heat loss around the insulation if it is. Membranes used in wall construction may also be subject to fire performance requirements, depending on the project, and this is especially true of membranes used in this location. Although Regulation 7.2 requires the main materials which become part of an external wall of relevant buildings to have a fire classification of A2S1D0 or A1 in accordance with BSEN 13501-1 2018, there are several exemptions granted in Section 12.16 of Approved Document B, Volume 2, Section B4. From the approved document, a relevant building means a building with a story, not including rooftop plants areas or any story consisting exclusively of plant rooms, at least 18 metres above ground level and which 1. Contains dwellings, 2. Contains an institution, or 3. Contains a room for residential purposes, excluding any room in a hostel, hotel or boarding house. In this definition, above ground level in relation to a story means above ground level when measured from the lowest ground level adjoining the outside of a building to the top of the floor surface of the story. Of relevance to our discussion today is 12.16a, which states, membranes used as part of the external wall construction above ground level should achieve a minimum of class BS3D0. This exemption is partly in recognition that some materials such as vapour-permeable membranes may not be able to achieve this fire class whilst maintaining sufficient vapour permeability. A similar exemption is provided in the Scottish Technical Standard 2, but the cut-off point for a construction to be considered as high-rise is lower in Scotland, at 11 metres as opposed to 18. These exemptions allow designers a little more flexibility to balance fire performance against other project requirements, but it is especially important that the fire classifications and testing are up to date and based on relevant test criteria. Fire testing information and certification for materials should be available from system suppliers. The placement of the air and vapour control layer or layers within a building should be considered in the wider context not just of the transfer of heat, air and moisture, but also with regards to installation practicalities and long-term robustness. As performance levels in terms of both fabric insulation and envelope airtightness increase to the level required by the Passive House standard, minor defects in construction can have a far greater impact on the long-term as-built performance. Because of this, designers increasingly must consider not just how to design structures which offer the best theoretical performance, but also which can be constructed in the simplest and most durable manner. The last of the passive principles is the use of ventilation with heat recovery, in which heat from extracted airflow is recovered through a heat exchanger and fed back into the building via the incoming supply air. This improves the efficiency of the building by reducing heat wasted by the extract airflow, and such systems are generally required as part of the Passive House certification. Without heat recovery ventilation systems, it can be difficult to meet the space heating energy requirements. When using this kind of system, it's important to ensure end users are made aware of maintenance requirements. Most MVHR systems will require regular filter changes and other servicing to ensure they're operating correctly. These requirements will vary between systems, however, so specific advice should be sought from the supplier of the specified system. This requirement in the Passive House specification often leads to an incorrect assumption that all airtight buildings require mechanical ventilation. If designers are not working to the Passive House certification specification, then various other options for both ventilation and heat recovery are available. In fact, it's perfectly possible to have good indoor air quality at low air leakage levels with a fully passive ventilation system, provided this is designed into the building early enough. What is important here is ensuring the buildings as built meets what is specified. If you design the building heating and ventilation systems to operate with an air leakage rate of 3 meters cubed per metre square per hour, but when tested the building only achieves 7, then problems can arise as highly optimised heating systems may not be able to compensate for this shortfall. Conversely, if you design to 7 meters cubed per square metre per hour and actually achieve 3, then ventilation may not be able to supply sufficient fresh air to provide acceptable air quality. What is important is ensuring the building is constructed within its design specification, thus allowing all the building systems, active or passive, to perform as intended. Heat pumps. A further possibility for the recovery of heat to lower the energy use in a home is to use a heat pump in the heating system. There are two primary types of heat pump, air source and ground source. Air-sourced heat pumps, or ASHPs, use heat exchanging fluids and compressors to extract heat from the ambient external air and supply it to the interior of the home, either via a more or less conventional central heating or underfloor system in an air-to-water supply system, or via warm air circulation in an air-to-air system. Ground-sourced heat pumps recover heat from collector loops buried underground. Fluid is circulated through these loops and picks up heat from the ground, which is then fed through a compressor and heat exchanger and used to heat the home. Both of these systems commonly use a large water tank to act as a heat store, using the thermal mass of the water to retain heat energy until it is required by the heating and hot water systems in the house. Ensuring this heat store is well insulated is a critical part of ensuring these systems operate efficiently. Both ground and air-sourced heat pumps are designed to operate at lower temperatures than fossil fuel or electric heating systems, and this lower operating temperature works particularly well with underfloor heating systems. These lower temperatures, as well as the lower running costs, mean these systems are typically designed to run continuously or almost continuously, and have less scope than traditional heating systems to boost their output and to meet additional demand. The better the energy performance of the dwelling they are fitted to, the more effective they will be. This makes these kinds of systems a good fit for low-energy homes. The relative lack of spare heating output also reinforces the importance of predictable and reliable energy performance at the specification stage, as the only practical solution to an under-spec'd underfloor heating system is often the use of auxiliary electrical or solid fuel heating, which may not be a good fit with an energy and ecology-focused project. That brings us to the end of today's presentation, and we'll now move on to the Q&A session. Good morning, everyone. My name is Kira Proctor, and I'm the Managing Director here at the A. Proctor Group. First of all, I'd like to thank everyone for attending. I hope you enjoyed the webinar and that you're enjoying this horrible Friday morning. Well, certainly it is here in Scotland. Believe it or not, this is our almost 60th webinar that we produced here at the Proctor Group, and we now have over 100,000 views of all the webinar content that we've actually produced. As you know, we'll stay here as long as it takes to answer all your questions, so please ask them either here on YouTube, you can DM us on Twitter, or you can email us at webinar@proctorgroup.com. If you'd like to request further information on any of the products discussed here or request a meeting with one of our team, you can do that now on our webinar page. Personalised CPD certification is also available on that same page. If you've registered, you'll receive a follow-up email with all of these links, plus a link to the replay. Late registration is still available on the website just now. A quick date for the diary. Our next webinar will be on Friday, the 14th of October at 10 a.m. Now the topic will be Design Solutions, Waterproofing and Gas Protection. We have a very special guest who is Richard Crossley, who is the Technical Director at Newton Waterproofing Systems. Now they are the UK's leading independent suppliers of structural waterproofing systems, and he will be presenting a webinar that covers the following topics: relevant updates to BS 8102 2022, waterproofing and ground gas guidance, and design solution. Finally, before we go on to the Q&A, it really helps us if you give us a thumbs up. So if you enjoyed the webinar so far, please like it, and also you can subscribe to our channel. That way you'll also receive updates about any other information that we're sharing or other events that we're doing that maybe you haven't signed up to in the past. So this week we have some familiar faces. If I can just introduce them one by one. We have our Senior Technical Advisor, Pamela Howitt. Morning, Pam.
Morning, Kira. Hi, everyone.
Morning. Sales Director, John Johnson. Morning, John.
Morning, everyone.
We also have a Business Development Manager, Adam Salt.
Morning, everyone.
Hi, Adam. And our Regional Sales Manager, Mark Blackie.
Good morning, Kira. Good morning, everyone.
Hi, Mark. Good. So, Mark, seeing as you're off mute, I'm going to jump straight into a question from YouTube for you, please. So, Haley Rose has asked, does my builder need Pacify certification?
Well, it's an interesting question. Not necessarily. They don't need to have a certification, but it would be recommended for them to have good building knowledge and to understand the key passive house principles such as airtightness and the importance of sticking with the specified products and installing with the right specification. But the Passive House Trust does have a members map if you're struggling to find an appropriate designer or a contractor within the UK. They've also got a list of international certified people along with training courses to become certified yourself. But all Passive House projects must be certified independently. So it's important to get everyone involved in the design and build and get them engaged at an early stage.
Okay, that's great. Thank you very much, Mark. Adam, Simon Wilson has asked quite a controversial one. I've heard this a lot, so I'm interested to hear your answer. Does a passive house have to look boring and like a box?
No, that's a bit of a misconception of passive house. I think that comes from passive house is very highly engineered. So in theory, a nice simple box design is going to be more efficient and also cheaper to construct. But that compact shape is similar for any type of construction. You can certainly have adventurous designs within passive house. The other thing is also the size. I hear quite a lot of people say passive houses, all small projects, small houses. That's certainly not the case. We're starting to see more high-rise passive house projects popping up. And I have to drop it in there. St. Sidwell's Point was certainly a massive leisure centre down in Exeter, which was passive house as well. So yeah.
I just read that case study in the Passive House Plus magazine. It was really interesting, actually. Not just the product we supplied, but the whole concept of it. It was fantastic. So recommend that.
It is, and hopefully we'll have a webinar on that later this year.
Good stuff. I've had one via email here from Rob. So Pam, perhaps I can come to you for this one, please.
Yeah, sure.
Given the adverse effect of thermal bridging on the U value of a timber frame wall insulated with rigid insulation, increasing it from 0.22 from 0.15, do you know what effect any gaps between the boards and rafters creating thermal bypass would have on a typical U value?
That's a good one for a morning. I'm not sure I've had enough coffee for that. Yeah, I mean, it's very difficult to take the thermal bypass effect and put that into a U value calculator. It's really when you're looking at sort of like solid bridges through it that you can add in. I mean, in theory, you could put in air gaps. There isn't a way, I don't think, of easily calculating it until you take it into more specialist software, possibly like thermal bridging calculations, like the psi value type software. But because it's not a repeating bridge, it wouldn't normally be taken into account in a standard U value calculation. So you are looking at a more sort of specific one, but it really, that is where the as design, as built kind of start to mesh. So you're designing it not to have those gaps. So it's really important to manage the site control aspects of it and the quality install parameters to make sure that you don't actually have that occurring. And using things like airtightness membranes are going to help limit that, because that's going to stop air actually getting into the air to circulate in the first place.
Good, thank you. Pam, another one via email, if I can just come to you again, please. Nathan has asked, can you help with an issue of cold bridging I've got on my project? There are large steel beams supporting the structure and we're struggling to detail them.
Right, yeah, this is coming in more and more because people are trying to build larger open spaces, and there's quite a bit of steel work going in. So we see this quite a lot. The space therm insulation is ideal for this because it is a very thin, high-performing insulation, and we do it in various components, either wrapped in film as cold bridge strip, which is great for the inside because it's got that sort of integral vapor control layer in it. And there's also a wrap therm, which is where it's bonded to a wrap tight, so you get that adhesive nature as well as the air permeability, and that makes it particularly good for external applications. So, you know, space therm is ideal for that. What you have to be careful is you don't just like pack loads of it on or put it on either side. Going back to what I mentioned in the previous question, you can do psi value, you can actually do like thermal bridging calculations, and they're actually quite important to do because what that does is it assesses whether you need the insulation on one side or the other side, or whether it's more advantageous to have a small layer on both sides. What you really don't want is a point where, say, for example, you insulate it both sides, but the bottom section of your steel is still cold enough for condensation to form. We've done quite a lot of studies on this, both on roofs and walls, and actually our technical director, Ian Fearnington, has just recently done like a white paper type document, which goes into this in more depth. So actually you can get that onto our from our website now. But it's really about balancing it and making sure that it's the right, but yeah, space therm is a really good one for that without being too bulky.
Good. Okay, fantastic. And actually, when I did my garden office, I used it on the steel beam. And we don't have a case study, so I know I'll get in trouble for that, but we'll get that done in marketing, I promise. John, I haven't forgotten about you. We have one here from Greg Robertson. Do all timber frame companies manufacture passive house kits?
That's a good question. No, what you'll find is that many of the manufacturers, they'll manufacture two passive house standards, but they'll have their own accredited systems. So it could be foam injected panels, it could be full fill panels with mineral fiber. It's probably worth checking with the manufacturer if you want to have a passive house specification. They probably can get that through the certified bodies, but it would be worth checking with your independent timber framers local to you to find out what systems they actually utilize. That can be found on the web. There's the STA, which is the Structural Timber Frame Association, and the ITFMA, the Irish Timber Frame Manufacturers Association, and you can pull that information on the website and have a look at the various systems that they promote.
Okay, good. And just while we're talking about resources, not in reference to timber frame, there was a good comment on here from Brian saying you can also look at the AECB, which I would agree with, for recommendations on builders and best practice. So another really good resource if any of the viewers haven't heard of it or hadn't noticed that on the YouTube feed. John, can I stick with you for one more, please, from Sean? Can installing more insulation help you achieve a passive house?
It will. If you're going for passive house standard, it will, but it wouldn't be classed as a passive specification by putting more insulation in. These passive standards are achieved by taking a holistic overview of the actual project, ensuring that you've got the correct amount of insulation, the correct type of insulation, and that these are all calculated in conjunction with the air tightness levels. You're really looking at having a holistical approach, excuse me, on the heating renewables, what solar panels you're using, if you're using ground source heat pumps, the orientation of the building. These are all taken into consideration when looking at a passive house specification and standard to achieve that level.
Good. Thank you, John. Pam, a good one here. I know that you're involved in various committees. So the BS 5250, there's a question here from Ray, who I believe is from Saudi Arabia, so welcome to our Scottish webinar. Does BS 5250 define particular airport terminal airtightness? It's more stringent than other building occupancies. And he followed on with a comment, is there more concern as operations go 24/7, and also higher fire resistance rating is a must, plus the noise reduction requirements. So quite a big scope there, Pam, if you can help with that one.
So BS 5250 is predominantly dealing with the management of moisture in buildings. So it doesn't really touch on anything to do with air tightness levels or what's required. That is probably going to be dictated more by the overarching legislation for that type of building. So, for example, the building regulations over here, it could be a specific school legislation or residential building legislation. So it is certainly not contained under 5250. But you're absolutely right. I mean, things like airports are massive users of energy. So anything that you can do to minimize that or to maximize efficiency of what you do use is definitely worthwhile looking at. And, you're right, things like fire resistance and noise reduction and isolation from the outside are all things that kind of go hand in hand with making energy efficiency there and adding an insulation. But it's a little bit out with, our scope here, but it's certainly not covered at all within the auspices of 5250.
Okay, thank you, Pam. And just on that, Ray, I noticed that obviously you have an airport project. We do have a lot of solutions. We've supplied a lot of projects in the Middle East, specifically airport terminals and various. So please pop us an email and we can certainly have our export guy discuss that with you in more detail. And he's very au fait with the region, so he'll be able to help with that. Okay, Mark, if I can come back to you, please. A question from John. Is the Passive House standard only applicable to houses?
No, it's a bit of a misconception, really. It can be applied to both residential and non-residential projects, such as schools, commercial, and leisure. And as Adam mentioned earlier, we've been involved in the UK's first passive house leisure centre, St Sidwell's Point in Exeter, where we supplied RIBA as an airtight membrane to achieve the required airtightness. We've also been involved in a couple of new build passive house schools closer to our head office, where we're using RIBA for airtightness. So there is passive house criteria that can be applied to a whole array of construction projects.
Okay, that's fantastic. Thank you very much indeed. I've got a few more in here. Adam, maybe I can come to you for this one from Ensign Design, an earlier one of theirs. So whilst possibly outside the scope of this presentation, does passive house certification consider embodied carbon in materials used?
Good question. Probably one we'll discuss a bit later on, but passive house doesn't include embodied carbon analysis, but it does sort of encourage to optimize embodied carbon, is so looking at through your whole materials of use. It's a big sort of part of looking at passive houses being energy efficient, so it kind of goes hand in hand with each other, but it doesn't have a embodied carbon analysis within it.
Okay. Thank you, Adam. And again, while you're here and on and live, George has asked, how do you heat a passive house?
Difficult question. I mean, it's a good question though, because a lot of people think you don't need to heat a passive house. You do need heating. It's just a very small amount. A lot of, if you're going down passive house, a lot of the route with heating will probably take down renewables. So maybe an air source heat pump would be a good solution, as opposed to maybe a ground source heat pump, which might be a bit of an overkill on a passive house type project. I've heard gas boilers even be used, again using minimal amounts on passive house, but I think one of the most common one is that I was even speaking to our technical director about the other day, is maybe having electrical heaters. You'd probably only need them downstairs on for a very short period of time, and that'll probably heat the whole building quite quickly, and if you get the ones that can move, that could be quite beneficial, but you'll be using minimal amount of heating, whatever system you use.
Good, thank you. Pam, Ensign's also asked, would you recommend against using rigid PIR type insulation between timber studs due to potential for gaps and also lack of hygroscopic quality, or would a super vapor barrier membrane help?
Yeah, it's a good one. I mean, to use Ian's favourite terminology in techies, it depends. PIR, phenolics, rigid insulations are all really good, and actually there are some very, very good technical arguments why you would use them, because you can get a very highly efficient envelope with, like a thinner amount of insulation, and it's quite cost effective. So it can be a good trade-off there, even though it might take more energy. Obviously uses plastic and hydrocarbon type oil-based materials. It is very much on that install side of things. So, things like gaps can be mitigated by using squeezy foam or fillers in between it. You can mitigate some of it by possibly having like 2 layers and offsetting. So you're staggering joints, taping joints, etc. can do it. And very much the vapor control layers and the breather membranes that you use are really important to control that movement of moisture through the walls. So it might be that one particular type of membrane, like our ProCheck, for example, or a reflective therm, would be more applicable to be used in this situation from the moisture control aspects. But as long as it's all sort of designed to go well together and assessed to make sure that there's no risk of condensation, again, it comes down to quality control, which really is at the heart of passive house full stop. You can do a very, very well installed PIR, but you can also do a badly installed mineral wool. So, where it slumps and you've still got that problem, if not more so. So it's to coin James Brackenreid Johnson's favourite phrase, it's the devil is in the detail.
Absolutely. Well said. Thank you
Can I
very
just
much.
add to that? I think that's why we've seen a lot of shift to off-site now, because of the tolerances within a factory environment to improve those installs and to achieve what Pam's just said, basically.
Good. Really good point, Adam. Thank you very much. So Adam, you've nominated yourself for another question via email we've had. Really good question. Are passive houses more expensive to build?
Yes, but I think not as much as people probably expect or think. I think there's actually been a couple of projects out there that are passive house built and are the same cost as a traditional build. But typically you're going to pay a premium of up to 10% for the higher quality build. But then you do also have to factor in, you've got the improved performances, that's going to improve the value of your property, and the most important thing, your reduced energy bills, especially at the moment. Yeah. Great point.
Great point. Okay, I have one in via email. Let me just find it here. Bear with me 1 second. From Tam. JJ, if I can come to you for this one, please. Does lining the internal face of the timber kits with 25mm foil-faced PIR eliminate cold bridging through timber studs?
It will. Yes, it will. We have quite a few timber frame manufacturers where they will utilize this rather than increasing their stud depth. They will put a 25mm PIR. We actually laminate these in our factory, so it saves on two points really. Labour point of view of having to fit a PIR board and then putting the plasterboard on. If you use a thermal laminate, then you're eliminating that cold bridge potentially all the way through the frame. So it's a detail that's used quite a lot by quite a lot of the builders in Scotland on timber frame as well.
Okay, that's great. And you do know a lot about timber frame, especially in Scotland. I agree with that. And just John, another one for you. Oliver's asked, are any of your products Passive House certified?
Yes, we do have products that are Passive House certified. You can download these from the website or contact our tech desk, and they can carry out calculations and advise you where these products are and where to install them. Give you installation guideline details for that as well.
Okay, thank you very much. Mark, Jess has asked, great question, can I turn my existing home into a passive house home?
Oh, well, yeah, yes, you can. There is a kind of a dedicated standard in relation to passive house known as the NFIT standard. Now, that standard gives you a little bit more movement in achieving certification. But in essence, what you'd be looking at are things like heat recovery and ventilation, high performance windows, high specification insulation, be it internal or external, air sealing the envelope, as we've mentioned, and also addressing thermal bridges. In actual fact, we've got a webinar on NFIT on YouTube covering this in quite some detail, and we can put a link in the comments for those who are interested.
Great idea. Thank you very much. Okay, let me just go back to my email ones. Sorry, guys, I'm on a few different systems here. In fact, I can't find one. So Ensign Design, Pam, does Passive House credit high thermal mass insulation?
Yeah, sorry, just I saw that one coming in, so I thought I'd have a little bit to think of that. It certainly is very important in the overall strategy for the building, because high thermal mass means that once you bring the building up to heat, it almost acts like a storage function. So therefore you can turn down or reduce the amount of heating or energy that you need to do that. And certainly for people who are maybe in that building all the time, so, families with young children, older people, having things like thermal mass is really important, because then that means that they get thermal comfort throughout the day. Single people or families that come in and out and dot in and out probably want a quick instant heat, so maybe that isn't so suitable for them. So I think thermal mass will certainly be taken into account as part of the full design process. Whether you would be scored extra allowance for having good thermal mass in it, again, it will depend on the type of building it is and the fabric. It's not a bad thing to consider from the whole energy aspect and reducing your embodied energy used in the building.
I think it's a great point to consider what that building's going to be used for and what type of course, the families may change over the years, depending on who lives there, but great answer. Thank you, Pam. Thank you very much. Adam, I finally found the ones coming about from email. So Matthew has asked, would Raptite alone be sufficient for a SIP build, or would you recommend an AVCL internally as well?
Okay, it kind of depends. So if you look at an air and vapor control layer where it performs that dual function of being airtight and vapor tight. So from an airtight point of view, with Raptite going externally on a SIP panel, that's your airtight line, well nicely secured. Already SIPs are very good already, and then you've got the secondary line with the Raptite. It's all just about seeing whether we need it for vapor management from that point of view, which could be done by a couple of calculations, depending on, again, the types of SIP systems we're using as well, because there's a few different manufacturers out there. But we can certainly look at that on a project by project basis. Yeah,
I agree. Having built a SIP home, it's not as simple as you use one or you don't. You do have to go through the steps to check.
And if I remember right, you used the reflector firm, was it internally?
Yeah, we used that. Yeah,
so
we did.
You got the added benefit with the air gap in front of it firmly for that.
Absolutely. Yeah, so we've got the thermal benefit from that.
Yeah.
And Adam, if I can stick with you, please, can I open, you're getting all the awkward ones, can I open a window in a passive house?
I think you've had this one before on another webinar.
I'm sure I have, yeah.
It comes up quite a lot, and you certainly can. I think that the question is sort of why. You have these mechanical ventilation systems along with the airtightness, and that ensures a good indoor air quality regardless of the weather. So I think it's more that the occupants are less likely to open their windows. If you think about when you're at home in the summer, you open your windows and then you go to your office where all the windows are closed because it's nicely ventilated, and that you're not required to do it, and the air quality is already good. And it's quite interesting speaking to an architect the other day. They were saying, think about when you're in a heat wave and you do open those windows in your house, you just kind of try to get that warm air out by letting warm air in. So actually the ventilation systems kind of help with that to ensure there's good levels from there.
Good, thank you very much, Adam. Okay, we're coming towards the end. I've got a few more. I think I missed an earlier one on YouTube from Marissa, apologies, from Marina. So Pam, can you build airtight with natural ventilation?
Yeah, we sort of touched on that earlier on, and we did, Adam, sort of nicely segue into that. It is possible to do it, but it has to be taken into account right at the early design stage. You can't sort of suddenly get so far down the line and try and switch back to natural ventilation or vice versa. Traditionally, the more airtight you go, you really do have to have an MVHR system or some sort of exchange system. And those particular systems do tend to work a lot better, the more efficient and the more airtight your building is anyway. However, there are some very clever companies out there that are doing some excellent work with developing passive ventilation systems, and those passive ventilation systems often have heat recovery. So you're getting the best of both worlds. You're bringing that back in. So it can be done with natural ventilation and purge ventilation, etc. But it's really important to engage with these people and know that that's what you want to do, and use that as a basis for your design rather than trying to shoehorn it in. And it's kind of a really important thing about passive house throughout is that once you design something, stick to it. You can't suddenly sort of chop and change as you want. So yes, it can be done, but it needs to be considered at an early point in the design.
Good. Okay, I think I have two more questions. So if anyone has any more, please post them now on the YouTube feed or Twitter or email. I will pick them up somehow. So John, Prashant's asked, can I use space therm air gel insulation for cold roof of the loft dormer? I have an issue for internal loft height.
Okay, yep, that's another good question. It's one we do come across quite a bit with dormers. It'll depend on whether it's a new build or a refurbishment. If it's new build, then you've got the opportunity of putting a roof shield membrane over the roof, which means you don't require that 50 mil airspace between the membrane and the insulation. So you can actually pack the insulation hard up into that. So that's going to give you a thermal benefit. If it's existing, then yes, the aerogel product we can layer that and cut it to the exact size that you require to fit in between your rafters. Another key benefit with the aerogel products are that because they're such low thermal conductivity and give really good thermal performance, you tend to limit the amount of overheating you can get, because certainly I know people in the past, with dormers, room in the roof, you can get it very, very hot in the summer. So it'll help control that temperature coming back into the room during the night when you're trying to sleep.
Very good point. And there are a lot more rooms in the roof now that we're seeing in the UK.
Yeah.
We're following the European trend. So, okay, Pam, Max has said, I've been looking at various membranes and types of insulation for my low energy builds. Can you give any idea of what membranes work best with what insulations and any do's and don'ts?
Okay. Again, it depends on what construction you're going with and what you want to achieve from it. But a sort of a general rule of thumb would be that if you are using a rigid insulation like a PIR or phenolic, then they tend to be quite high resistance. They don't have the hygroscopic that we talked about earlier, that sort of ability to buffer moisture. Therefore, you want to use kind of pretty static vapor control layers like our Reflectitherm, ProCheck 500, etc. And on the outside, your standard breather membranes like your Wrap-Tite UV, depending if you've got open joint cladding. So, the combination of a static higher resistance insulation, the higher resistance higher resistance insulation and breather membrane means that you're controlling the amount of vapor that can pass in there. If you're looking for a more breathable, more permeable construction, and you're using things like more natural insulations like sheep's wool, hemp insulation, wood fibre insulation, then these really do benefit from using what's called the intelligent membranes, so the variable humidity membranes. So depending on temperature and humidity levels at the time will depend on whether these are more vapor open or vapor closed. Tend to all be airtight anyway. So something like our ProCheck Adapt internally with the Wrap-Tite externally, and your mineral wool wood fibre between is really, really good from that moisture, because you get a bit of moisture buffering and everything. And it's also worth knowing for those that are doing passive house is that both the Wrap-Tite and the ProCheck Adapt are both certified under the Passive House scheme, and they're both A+, which means that they're really good for airtightness.
Fantastic. Now, you mentioned Wrap-Tite there. Last question, which just came in from Rachel. So I'll stick with you, Pam, if that's okay. What sort of problem areas should I look for when detailing my Wrap-Tite for the external airtightness line?
Yeah. The big one that we always start with is prep. Make sure that your surfaces are smooth, not lots of rough nodules or undulations, because you're going to then struggle to get things to bond to that. And make sure any nail holes are filled up, any protrusions are ground flat or taken out. Consider how you're going to look at any plenums or ducting and make sure that you can actually either work around that so there's space. Quite often there's not, so perhaps you need to look at doing something to that area before you actually put that duct in. Things like split liner Wrap-Tite tape is ideal for that, where you can peel off one side and fold it in and get into small areas, as is our liquid flashing. In terms of performance, the big one with both the Wrap-Tite and Wrap-Tite UV is making sure that you remove bubbles, and certainly don't have any of those bubbles breaching the overlaps where you can have wrinkles. Because if you've got bubbles that at the joint, you've basically got to a point where air can leak and water can get in. So it's make sure that you don't get that, so you don't get the lateral bypass of air behind the membrane. Make sure all the edges are well installed, well rollered down, and take time. Don't just go rushing in there. Take time to look at what you're doing, what you need to do, assess it, and don't be worried if what you start with evolves into something else, because as you work with it, you will develop skills and knowledge as to what works well in your build. So it's start on the easy bits and then go to tackle the hard bits, but always have those hard bits at the back of your mind, and make sure that any scuffs, tears, rips, damaged holes, all these things are sealed up and repaired before you get your airtightness test, because that all contributes to the overall leakage. If they're damaged, you could have a point of air leakage at those areas.
Absolutely. Thank you very much, Pam. I noticed that someone's asked for John's contact number and contact details, and he apparently can't spell his own name. So Proctor Group have corrected him. Have it under good authority, mind that he is very proficient normally. So just maybe not so good at typing on the phone whilst he's trying to do something else. Okay, now very lastly, this is just a comment we've had, and I wanted to throw out to the panel. From an architect, just saying that it's probably worth noting that to achieve Passive House certification on new builds, consideration should be given to at the outset to form factor and building orientation, as well as fabric design and efficient services. So I just thought it was a really good point. I wondered if anyone had anything additional that they wanted to kind of follow on and comment on that.
Yeah, absolutely. Sorry, I'm going to jump in. It's absolutely true. One of some of the principles of Passive House is making use of natural solar gains to provide the heating, and also overhangs and locations for purging that heat as well, so that you don't get overheating. So it's not just about building the fabric right, it's about the placement right and the location right, to running the ducting correctly, and making sure that you just follow all the steps. So it's a really, really great philosophy and a really great package that they've got. It's really important that you're going to commit to 100% and take all these aspects into account.
Yeah, I was going to say similar. I mean, we talk about it a lot in presentations. We start off with the building's purpose, the occupants, then we move on to the external environment, and that includes everything like the position of the building, the solar gains, the sheltering, exposures, and then we move on to how we're actually going to build it on site, off site, and materials we're going to use. And that's a big part of our philosophy at Proctor's.
I think it shows the importance of speaking to a Passive House architect or designer that knows what they're doing, because they have a wealth of knowledge that they've built up from making mistakes, probably the same as everybody else does, and get their advice.
One area that we've also seen a big interest and increase in requirements is for our wrap therm, which is the aerogel laminated to the wrap type product. We've got quite a lot of people now who they're looking at their solar gain, so they're building these massive bifolding doors that can be glass doors up to maybe 5-6 meters to get the benefit of that solar gain. But you've got a big steel lintel in there. And the problems in trying to insulate that with rigid insulation. So we can cut and fit these products, the wrap therm, to the exact size and dimensions of these steel beams to completely eliminate that cold bridge.
Yeah, exactly where I used it in my project. That will be a case study forthcoming for our marketing. Mark, did you have anything to add?
No, just highlighting Adam's point there, really, about in terms of looking at the building fabric, the occupants, and the location. It's kind of key to Passive House design, really. So yeah, absolutely, it's as a holistic view.
Good. And I was going to say as well, this house, you can obviously see quite a lot of glass behind me. My husband and I built this house 3 years ago, and there's more glass here, which is these big bifolding doors that John's talking about, and around the corner. So there's a lot of glass, and people often say, does it not get really hot in here? Does it not overheat? And like that, this isn't a passive house, but it's a very low energy home designed by a low energy architect and designer who also is Passive House accredited. But the overhangs are probably the most important decision-making part of this house. And I think we'd be in a lot of trouble if we didn't have various overhangs, just based on, because it gets the sun all day. But there is actually a webinar on that if anyone's interested. I think it's titled Self-Build, and it's a case study about materials used and how it was done and whatnot. So please have a look on our YouTube channel and feel free to watch it. I got some interesting comments, mostly positive, and some critical about my house, but you can't please everyone. So there you go. Okay,
that's one of the key things. Sorry, quickly on houses. On houses in general, they're a bit like cars. If you've got a young family with kids and dogs, and the back door and front doors are open and kids are in and out, and you've got the exact same specification of house next door that's got an elderly couple that are maybe out in the morning, they're in, they shut, they keep their doors locked for security purposes. These houses are going to perform completely differently, very similar to a car. You give an old man a sports car, he'll drive it sensibly. If you give a young man a sports car, he'll drive it like he stole it. So you're not going to get the same performance and energy consumption out of them.
Or women, yeah. Or women.
I was about to say, John.
Good. Okay, well, listen, thank you very much for attending, everybody. We've now come to the end of our questions, and I don't think I've missed any today, because often I do and I have to email someone back, but I've been quite diligent, I think. So hopefully I have got everyone's questions. If not, then you will be contacted. So again, just a quick date for your diaries. Please put in the Friday, the 14th of October, 10 a.m, the same time. Now, it's not RIBA accredited, this one on the 14th. However, we do have a special guest who is the Technical Director at Newton Waterproofing Systems, a chap called Richard Crossley. And he will be talking about relevant updates to the new British standard, BS 8102 2022, waterproofing and ground gas guidance and design solutions. Personalised CPD certification is available for today's webinar on our webinar page. So that's proctorgroup.com/webinar. And you can also request further information, a meeting with one of our guys here or girls here, or various staff, and we can come back and help you. It helps us if you give us a thumbs up if you enjoyed our webinar today, and please feel free to subscribe to our channel to see future webinars and other content that we share frequently. So thank you very much. Wishing everybody an absolutely lovely weekend, and I hope you get better weather than us here up in Scotland, and hopefully we will see you on the 14th of October. Thanks, guys.
Thank you.